Today on statistical methods for open set recognition. Brief recap, in the first part we looked at the open set recognition problem. We motivated the problem, tried to understand why it's so difficult, and we started to introduce some nice theory that can help lead us to algorithms. In the second part of the tutorial, we're going to look at statistical extreme value theory as one of the building blocks to move into an algorithm. I'm sure most of you are not familiar with this branch of statistics, as you typically don't see it applied very much in computer vision. Though we're trying to change that because it turns out to be very, very interesting and useful. And I'll explain why in the next segment. Mark's raising his hand. Typically you find extreme value theory in other branches of engineering. We find it a lot in manufacturing where it's used for lifetime analysis. When is this part likely to fail? That's a question that extreme value theory can help us answer. Also disaster modeling, you know, when is the big flood going to happen? How probable is that? Based on prior evidence. You see statistics like this popping up, and also a lot in finance. And that, in fact, was kind of the motivation for a lot of our computer vision work. Unfortunately, the investment banks don't like to publish too much on what they're doing with it, trade secrets and whatnot, lots of money at stake. But I'm going to talk a little bit now about what this is and why you would use it instead of something like basic central tendency modeling, applying Gaussians like we typically do in computer vision. So it's a powerful explanatory theory, and we've published a few papers explaining why, and I'll kind of touch on that. But most importantly, I think for our purposes in the open set recognition world, it's a very effective tool for statistical modeling of decision boundaries. And we'll explain why. And we're finding it now as a useful tool for calibration models, for supervised machine learning, and we can also apply it inherently in the objective function of supervised learning algorithm itself to do the learning component as an alternative to other things like kernels. So what is the extreme value theory? It comes back to this extreme value theorem, which is quite old. This goes back to the early 20th century. Statisticians were trying to understand what do you do when you have some sampling of extrema. There are many problems where we have this, especially in computer vision, where we're sampling maximums or minimums. Do the same distributions we use typically apply to those extrema? As it turns out, no, there's a whole set of other distributions you should apply when you're sampling extrema. If you think about tail modeling problems, this is where this comes into play. The extreme value theorem basically tells us if we have some sequences of IID samples and we have some maxima that are drawn from these samples, if a sequence of pairs of real numbers exists such that this expression is satisfied, we end up with a special distribution. It turns out that f is a non-degenerate distribution function, and it belongs to one of three extreme value distributions. The Gumbel, which sometimes we see in machine learning for sampling problems, Frichet, which I rarely have ever seen applied for any useful purposes, but it's one of the three distributions, and the Weibull distribution, which is what we're going to evoke quite a bit in the rest of this tutorial. And depending on the constraints of your problem, that's how you choose one of these distributions. So if your data are bounded from, say, above, you would apply the reverse Weibull, which is actually the third extreme value distribution coming out of the theorem here. Of course, there's this problematic constraint of IID samples. In computer vision, you never have those. But you can relax some of these constraints to a weaker assumption of exchangeable random variables, and these distributions we found approximately apply in most cases. So a little bit more about the Weibull distribution. The Weibull data, as I mentioned, are bounded. So if I have a reverse Weibull, they're bounded from above. If I have a Weibull distribution, the data are bounded from below. And I must invoke this distribution. It has either 2 or 3 parameters. Here I'm showing you the 2-parameter form. I'll have some scale lambda and a shape kappa. I might also have a position, which I think we call tau in the rest of this talk. You may see the 3-parameter Weibull invoked. The choice of this distribution is not dependent on the model that best fits the entire non-matched distribution. This is something that's going to be important when we talk about a modeling technique we call meta-recognition. later on in this section. Another thing to note too about the extreme value theorem, you can think of it as a limiting distribution similar to the central limit theorem, but it applies to extrema. The more we keep sampling extrema, the more likely it is we're going to converge to one of these distributions. And so that's an important note. Fitting an EVT distribution, again, it's not central tendency modeling. We're going to sample something from the tail, some number of points, and the EVT is going to apply regardless of the overall distribution. So we could imagine having a Gaussian distribution. We sampled extrema from it. One of these other distributions applies, not the distribution that fits the overall data distribution. And we could have complicated multimodal distributions. It doesn't really matter what that original distribution is. We only care about the right distribution for the extrema. So is there a difference between central tendency modeling and EVT? This is a key question because there's always a lot of confusion when it comes to the probabilities that come out of the models when you say do central tendency modeling versus extreme value theory modeling. So let's walk through a little example with some simulated data. Imagine that we're going to sample a set of 1,000 values from a standard normal distribution, so nothing secret or tricky about that. And then we're going to compute means over 10,000 trials. What does the histogram look like for this? Any guesses? Yeah, exactly. It's familiar bell curve. Whoop, that's exactly what we expect. Now let's think about this with respect to the extrema from those samplings. So let's do the same thing again. We'll sample a set of 1,000 values from a standard normal distribution. And this time we'll retain the maximums over 10,000 trials, not the means of those samplings. Any guesses? What does the histogram look like here? Okay, Mark is cheating from a prior. But I think the guess will say it's not going to look like a bell curve per se. Notice that this peak is now at 3.2. There's a shift here, and there's a noticeable skew in the overall distribution. This isn't what we'd expect if it were a Gaussian. And so something has changed here, right? The nature of the data are different. Probability estimation. So let's just ignore that for now. And let's think about generating probabilities from those samplings. So I can take R, which is a nice statistical toolkit. I will do the same procedure I just described. I will sample and compute means for 10,000 trials. I'll get that nice Gaussian bell curve, and then I can assess probabilities from that, looking at the CDF. There are 3 points here I'm looking at the probabilities for: 0, 1, and 2. If I had 0, right, 0 is the mean of that distribution, so it has some likelihood which is plausible, right, 50% roughly here. Based on the data we've sampled. But if I go to 1 or 2, this model is showing me that these are basically improbable. These numbers can't apply with any degree of certainty. They're far out on the tail. It's improbable to get them based on this model. But I can go back and I can fit an EVT distribution. In this case, I just did the generalized extreme value distribution. Here I have different parameters. In the previous model, we had our standard deviation and our means, right, which is the parameters for a Gaussian. Here I have location, scale, and shape, which are found in various instantiations of extreme value theory distributions. And I've created this model here, the numerical values for the parameter. And I went back and I tried the same values I tried before and then a few others. So notice now 0 is still probable, in fact is highly probable of occurring with this particular model. But then I brought back in 1 and 2. They were improbable in the model we showed you before, but now they are highly probable based on this CDF from this fitting. Right? Because we targeted a different part of the distribution, we targeted these extreme values, and we fit an appropriate distribution to them. Why is this important? Why do we care about this? Depending on your model, you can get very different probabilistic interpretations of data. So you can imagine if this was a flood situation you were trying to model, your Gaussian model was saying the big flood will never happen. It's improbable, right? It's 0%. But if you looked at extrema from samplings of previous floods, maybe that big flood is probable. That's a big change in terms of the modeling. And so this is kind of the motivating factor for using extreme value theory in a number of different fields. Again, lifetime analysis. If you're trying to model the failure of an aircraft, most of the operation during the aircraft's lifetime will be fine. You don't have to worry about things. But there are these rare events, at the beginning of the aircraft's life cycle and at the end, where you see catastrophic failure. That's the most probable section of the lifetime where you may see failure. And if you use the wrong probabilistic model, you seem to have no probability of failing in the tails of the lifetime distribution. But you move to EVT and you see you should be worried on those first few flights and those last few flights, because that's where accidents tend to occur with non-zero probability. And so this is the motivation for us sort of using this in computer vision and for decision boundary modeling, because we know in some of these cases near the decision boundary, the central tendency model will tell us this is improbable, you're too far away, but we really want a good understanding of class association even near the class boundary. And so EVT helps us with that. And to kind of sort of drill that home a little bit more, here are some visual depictions of various distributions. Imagine we have a binary classification situation. We have two classes, class y sub 1 and y sub 2. Y sub 1 here is the red circles, y sub 2 the green. Here is a binary discriminative model. This is very much the half-space problem we were talking about in the first part of the tutorial. Because we have this third class, which is the unknowns, labeled here with the blue circles. Here's a probability model. If I'm trying to distinguish between red and green, here's the decision boundary. This is great. High degree of confidence if this is signaling 1 for the green circles, y2, and then 0 for y1, which would be the negative class. But it's going to keep assigning really high probabilities for all those blue circles, so that's bad. So if we move to, say, a Gaussian model, and we get tails with drop-off, this could be better. But notice how broad this distribution is. We're still going to get false positives on both sides because the distribution is so broad in capturing some of those other points. If we move to an EVT fit, say a Weibull distribution, we get much sharper decision boundaries here in terms of the probabilistic modeling. And because of that, we don't have as much overlap. In fact, in this case, I think we have no overlap in this particular model. And so this is a much better alternative. And this plot is showing you the same sort of situation. Again, Gaussian model, we're going to bleed over, especially if we have, say, two visual classes that are separated by a gap. And we want to understand what the model should look like. How much should we fill in to generalize? Gaussians are spilling over, and the EVT fit's a little bit sharper. Extrema as visual features at a more basic level, why would we want to invoke extreme value theory? A lot of what we look at in computer vision tends to be extreme data. Remember in the first part of this tutorial I told you about feature separation and things of this nature. We're trying to throw out a lot of information because we know that information is tainted by noise or irrelevant to distinguishing visual classes. If you think about, say, the visual makeup of this room and looking for salient objects in the front of the room, like the wall doesn't really matter, right? There's a lot of pixels if we take an image of this front of the room, but none of this is really meaningful. We're looking at edge structure when we try to determine that there are objects here like this podium, this screen, maybe that speaker over there. And edges you can think of as being extrema with respect to the distribution of all of the pixels in the scene. So we throw away a lot of information and then we're doing very targeted sampling. And there are other cases in computer vision too where we're looking at, say attributes or atypicality with respect to attributes, characterization, emphasizing, overemphasizing or de-emphasizing certain visual features, part boundaries, very basic in computer vision, and even saliency. And so the idea here is a lot of the content isn't useful. We're throwing away most of it, and we're getting perhaps a sampling of extrema too, just in a visual sense. So how does this apply to computer vision? I gave you a basic statistical explanation of what's going on, and then we looked a little bit at some overarching motivation. Where we started with all of this a long time ago was with this idea of meta-recognition, which we say is recognizing when a recognition system is working or failing. Of course, in an open set recognition world, this could be quite useful because those failure cases might be instances where open set data has affected our classification regime in some negative way. It's important for threshold selection, failure prediction, and improving fusion. So again, trying to help us make better decisions. In terms of extreme value theory, how does it play a role in this idea of meta recognition? Again, knowing about recognition systems at some meta level. We have our overall distribution of scores, which I showed you earlier. We have some tail space here from this overall distribution. We can then fit an extreme value theory distribution to extrema from the tail, and then we can leave out data and start bringing it back in to do a hypothesis test based on probabilities. So extreme value theory applies to the type of data we're modeling. We can think about this as tail analysis. We can imagine scores are drawn from some generating process. In this case, we're describing it as a series of portfolios, each portfolio generating one maximum score. So again, those maximum scores would fall into the tails of the distribution. And with the right statistical modeling, we can get the right probabilities. But coming back in a more basic sense to this idea of failure prediction, can we recognize in some automated fashion if a recognition system result is a success or a failure? And if so, can we quantify the probability of success or failure? So looking at this example, is the system, any recognition system, likely to fail on this particular stop sign if our classifier is trained to recognize stop signs? Right, this looks pretty easy. It should be okay. But what about this image? I mean, this one looks a lot more difficult. The stop sign's buried in the background. It's not the most salient feature, which would be the train. So a priori, can we predict something about these images? That's typically the way this has been done before in computer vision. Characterize the image, but don't do the score modeling, which is what we suggest. Meta recognition, which will look at the outputs, not the inputs to the system for failure prediction, will do the following. Given some recognition result, perform a post-recognition score analysis using the EVT methods, and then based on the prediction of success or failure, take some kind of action. So if we're trying to improve the performance of our system, we might request operator interaction, we may perform fusion, we might ignore that data because we know it failed, it was bad, we may acquire more data. There's a number of things we can do, and this is quite useful. You can almost think of it, as another learning process in and of itself if you're trying to improve the system. You can think of it in a pedagogy type regime where it's like a student knows they're struggling with something. If the system, right, the teacher is telling them focus on this, maybe you should go back and focus on that. And so there's this iterative loop to help you make corrections. So failure prediction is not really appreciated as much as it should be, I think, in computer vision, but certainly quite important. So one particular work I'll highlight, Predicting Failures of Vision Systems, which appeared at CVPR 2014 from Devi Parikh's group. Learn conditions that cause target algorithms to fail. So here are some examples, just characterizing the visual features before they're classified. Is this going to be a problem, yes or no? You could think of this as some methodology for image quality assessment. So if you're familiar with the area of human biometrics, we often try to apply a quality metric to the images coming into the system and make some prediction about how well the system will work based on them. Terry and I have always argued that the scores are the only things that matter because things that intuitively look like they may be poor quality often produce a decent recognition result. So why don't you do the score analysis and not try to create a predictor? Because a perfect predictor might be a really great recognition system, and we know that's the struggle. So there's some sort of paradox baked into all of this. But this is an interesting paper, and it shows that you can root out bad images and try to improve classification performance in some sense.